In this video, we will find intervals of increasing, decreasing, concave up, and concave down for these two functions. If you appreciate the content, please give it a like. As we go through this problem, be aware that the domain is restricted to the interval from 0 to pi. The first step is to find y prime. So we go term by term. The derivative of x is 1, and the derivative of cotangent is negative cosecant squared x. That's just a memorized rule. Next, we need to find where y prime is equal to 0 and where y prime is undefined. So setting y prime equal to 0, that's 1 minus cosecant squared x is equal to 0. Adding cosecant squared to both sides gives us 1 is equal to cosecant squared x. I'm going to flip this around. Taking the square root of both sides, we have cosecant x is equal to plus or minus 1. Let's take the reciprocal of both sides of this equation. Cosecant x is the reciprocal of sine x, and sine x is the reciprocal of cosecant x. Obviously, the reciprocal of 1 is still 1. Sine is the y value on the unit circle, so sine x will equal 1 at pi over 2, and negative 1 at 3 pi over 2. Except for, you know what, let me be careful. We have those domain restrictions. Let me look back. Aha! We are restricted to the interval from 0 to pi. So that wipes out the value of 3 pi over 2. So we just have this one critical value. Now it's time to find where y prime is undefined. There will be places where y prime is undefined because cosecant itself is sometimes undefined. Remember, cosecant is 1 over sine x. So cosecant x will be undefined wherever sine x is equal to 0. You can't divide by 0. So we can find where y prime is undefined by setting sine x equal to 0. Sine is the y value on the unit circle, and sine is equal to 0 here at 0 and here again at pi. So that would be x is equal to 0, x is equal to pi. But those are the domain limitations and are not actually included in the domain. So really we can just throw these out. Set up a y prime sign chart like this using the one critical value that we have. Make sure you label the sign chart as y prime. We're only going to have one row because we only had the one factor. We need to decide whether this factor is positive or negative in each interval. We're going to do that using test values. Pi over 6 falls between 0 and pi over 2. So let's use that as a test value. I'm picking pi over 6 instead of, say, pi over 4 or pi over 3 because I know that cosecant is the reciprocal of sine x, and the sine of pi over 6 is 1/2. Nice and simple, no radicals. So plugging in pi over 6, we have 1 minus cosecant squared of pi over 6. Well, like I said, the sine of pi over 6 is 1/2. The cosecant of pi over 6 will be the reciprocal of this, which is 2. So therefore cosecant squared is going to be 4. So we're going to have 1 minus 4, which is negative. In the interval between pi over 2 and pi lies 5 pi over 6. So let's use that as a test value. In fact, since sine x is positive in both quadrants, the answer is not going to change when we switch from pi over 6 to 5 pi over 6. So it's going to be the exact same thing and therefore still be negative. Because we only had one row, this gives us the overall sign of y prime in both intervals. Since y prime is negative, we know that y will be decreasing in both of these intervals. We say y is not increasing anywhere on the interval from 0 to pi because y prime is never positive. Y is decreasing on the interval from 0 to pi over 2 and from pi over 2 to pi because y prime is negative. Since y prime is defined at pi over 2, it's equal to 0, the College Board would accept writing this as one big interval and saying y is decreasing on the interval from 0 to pi. This will probably turn out to be a point of inflection. So y is decreasing on this entire interval. A quick word about abbreviations. In my other videos, you will often see me use these abbreviations for positive, negative, increasing, decreasing, concave up, concave down, and because. I accept these abbreviations in my class, but to be clear, you are taking a risk when you use any abbreviations on the AP exam. That's because it's up to the discretion of the grader whether or not these will be accepted. Most AP graders are going to give you credit for these, but if you want to be 100% safe, don't use abbreviations on the AP exam. On the other hand, if you are pressed for time, it might be worth the risk. In order to find intervals of concavity, we need to find y double prime, the derivative of y prime. For some reason, students really have a hard time taking the derivative when the trig function has an exponent on it. So I'm going to do a little bit of a rewrite to make it more clear. Cosecant squared x means that cosecant x is being squared. So when we take the derivative, we're going to have to do the chain rule when we get to this part. The derivative of 1 is 0. So now comes the chain rule. First we take the derivative of the outer function, the red part. So the 2 is going to come to the front and make negative 2, and then the new exponent is a 1, which we don't have to write. We leave the inner function the same, cosecant x, but we multiply by the derivative of the inner function, which is negative cosecant x cotangent x. That's a memorized rule. Written in its original form, students often don't see that they need to do the chain rule like this, outer function and then times the inner function. Also, I recommend never multiplying by something negative like this. Students often forget about the multiplication and they wind up treating this as subtraction and getting the problem wrong. So instead, when you multiply by a negative, take the negative and put it to the front. A negative times a negative is a positive. Now we notice that we have cosecant x times cosecant x. So actually, y double prime is equal to 2 cosecant squared x cotangent x. Let's simplify a little further by rewriting everything in terms of sine and cosine. Cosecant squared x is the same thing as 1 over sine squared x. So 2 times cosecant squared x is the same as 2 over sine squared x. Cotangent x is equivalent to cosine x over sine x. And sine squared x times sine x is sine cubed x. So this is a good expression to use for y double prime. Now it's time to find where y double prime is equal to 0 and where y double prime is undefined. A fraction will be equal to 0 where the numerator is equal to 0. So let's set 2 cosine x equal to 0 and solve. Dividing by 2 on both sides, we get cosine x is equal to 0. Cosine is equal to 0 at pi over 2 and 3 pi over 2. But I need to look back and check the domain limitations. We're only defined on the interval from 0 to pi. So in that case, it's just going to be the x equals pi over 2. A fraction will be undefined where the denominator is equal to 0. So to find where y double prime is undefined, we set sine cubed x equal to 0 and solve. Taking the cube root of both sides, we simply have sine x is equal to 0. We know that sine x is equal to 0 when x is equal to 0 or when x is equal to pi. But these are the limits of the domain and are not actually included, so we can throw this out. Simplifying everything in terms of sine and cosine is turning out to be much easier than it would have been if we had stopped here and tried to find where y double prime is equal to 0 and where y double prime is undefined based on this expression. Set up your y double prime sign chart with your one critical value and the endpoints of the limited domain. Make a row for each factor. You could have made one row for the 2 and the cosine, but I like to really break things down because later it makes things really simple to follow. We need to decide whether these factors are positive or negative in each interval. 2 is always positive. So there you go. What about cosine? Cosine is the x value on the unit circle, so it's going to be positive from 0 to pi over 2 and negative from pi over 2 to pi. So that means cosine x is positive in this interval and negative in this interval. Cubing something does not affect whether it's positive or negative, so sine cubed x will be positive or negative wherever sine x is positive or negative. Sine is the y value on the unit circle, and sine is positive in both of these intervals. So the overall sign of y double prime is positive from 0 to pi over 2 and negative from pi over 2 to pi. We know that y will be concave up wherever y double prime is positive, and that's from 0 to pi over 2. Y will be concave down wherever y double prime is negative, and that's from pi over 2 to pi. We say y is concave up on the interval from 0 to pi over 2 because y double prime is positive, and y is concave down on the interval from pi over 2 to pi because y double prime is negative. In addition, y will have a point of inflection wherever y double prime changes signs. That's exactly what we see at x equals pi over 2. We say y has a point of inflection at x equals pi over 2 because y double prime changes signs. Now it's time to sketch the graph of y based on the information above. Let's start by dividing the graph into intervals using the critical values that we found. So that includes pi over 2 and, well, just pi over 2. That's our only critical value. Let's record whether y is increasing or decreasing in each interval. We found that y is decreasing on both intervals. Let's record whether y is concave up or concave down in each interval. We just found that y is concave up on the left interval and concave down on the right. Let's indicate whether y has any horizontal tangent lines. Y will have a horizontal tangent line wherever y prime is equal to 0, so y will have a horizontal tangent line at pi over 2. Let's put a little horizontal mark at pi over 2 to remind us to form a horizontal tangent line when we sketch the graph of y. The graph of y will begin and end with an open circle because the limited domain does not include 0 or pi. In the first interval, y needs to be decreasing and concave up, and it needs to finish off at a horizontal tangent line. So here we go, decreasing and concave up, and rounding out at a horizontal tangent line. In the last interval, y needs to be decreasing, but now concave down. And don't forget, we need to end with an open circle. So here we go, decreasing, concave down, and at the end, an open circle. And that's it for the graph of y. Let's do one more. Finding y prime term by term, the derivative of 18x squared is 36x, and the derivative of negative x to the fourth power is negative 4x to the third power. Factoring out a common factor of 4x, we have 4x times 9 minus x squared. This is further factorable using the difference of two squares. So we have 4x times 3 plus x times 3 minus x. Looking at the factored form, we can see that y double prime will equal 0 at x equals 0 from the first factor, x equals negative 3 from the second factor, and x equals positive 3 from the third factor. Normally, we would also have to look for where y prime is undefined, but a polynomial is defined everywhere. Set up your sign chart with the critical values in order from least to greatest across the top, and a row for each factor. Make sure you label the sign chart as y prime. We need to decide whether these factors are positive or negative in each interval. 4x is equal to 0 right when x is equal to 0. So this is the only place where this factor might change signs. 4x is going to be negative for values of x to the left of 0, and positive for values of x to the right of 0. 3 plus x is equal to 0 at x equals negative 3. This factor will be negative to the left and positive to the right of negative 3. 3 minus x is equal to 0 at x equals 3. So this is the only place where this factor might change signs. To the left, we have values like 0. If we plug in 0 as a test value, we have 3, a positive 3. So 3 minus x is positive to the left of x equals 3. To the right, we have numbers like 4. 3 minus 4 is negative 1. So 3 minus x is negative for all values to the right of negative 3. The overall sign of y prime is positive in the first interval because of the two negatives, negative in the second interval, positive in the third interval, and negative again in the fourth interval. We know that y will be increasing wherever y prime is positive. That's from negative infinity to negative 3 and from 0 to 3. Y will be decreasing wherever y prime is negative. That'll be from negative 3 to 0 and from 3 to infinity. We say y is increasing on the interval from negative infinity to negative 3 and from 0 to 3 because y prime is positive. Y is decreasing on the interval from negative 3 to 0 and from 3 to infinity because y prime is negative. To find intervals of concavity, we need y double prime, the derivative of y prime. Let's go term by term. The derivative of 36x is 36. The derivative of negative 4x to the third power is negative 12x squared. I'm noticing a common factor of 12, so let's just go ahead and factor that out. So that'll be 12 times 3 minus x squared. Y double prime is a polynomial which is defined everywhere, so we just need to find where y double prime is equal to 0. Y double prime will equal 0 whenever this factor is equal to 0. So let's set 3 minus x squared equal to 0 and solve. Adding x squared to both sides, we get 3 is equal to x squared. I'm going to flip this around. Taking the square root of both sides, we have x is equal to, and I started to say plus or minus the square root of 3, but I'm going to go ahead and split this up as negative radical 3 and positive radical 3. So you can clearly see that we are talking about two different critical values. Set up your sign chart with the critical values across the top and a row for every factor. Make sure you label the sign chart as y double prime. We need to decide whether these factors are positive or negative in each interval. Of course, 12 is always positive. So there you go. Let's use test values to see whether 3 minus x squared is positive or negative in each interval. For the first interval, let's use negative 2. So we have 3 minus negative 2 squared. That's 3 minus 4, which is negative. In the middle interval, we have 0. Plugging in 0, we just get 3, which is positive. In the last interval, let's use positive 2. We can just modify this slightly because it really is not going to change anything. Positive 2 squared is still 4, and we still will have 3 minus 4, which is negative. The overall sign of y double prime is negative, positive, negative. We know that y will be concave up wherever y double prime is positive. That's from negative radical 3 to positive radical 3. We know that y will be concave down where y double prime is negative. That will be from negative infinity to negative radical 3, and from radical 3 to positive infinity. We say y is concave up on the interval from negative radical 3 to positive radical 3 because y double prime is positive, and y is concave down on the interval from negative infinity to negative radical 3 and from radical 3 to infinity because y double prime is negative. In addition, y will have a point of inflection wherever y double prime changes signs. That occurs at x equals negative radical 3 and x equals positive radical 3. We say y has a point of inflection at x equals negative radical 3 and x equals positive radical 3 because y double prime changes signs. Now it's time to sketch the graph of y based on the information above. Start by dividing the graph into intervals using the critical values that we found: 0, negative 3, positive 3, negative radical 3, and positive radical 3. Now let's label y as increasing or decreasing in every interval. Remember, we found that y is increasing on these two intervals and decreasing on these two intervals. Now let's label y as concave up or concave down in every interval. We found that y was concave up between negative radical 3 and positive radical 3, and y is concave down outside of that interval. In addition to this information, we need to find where y has a horizontal tangent line. Y has a horizontal tangent line wherever y prime is equal to 0, and that's at x equals 0, x equals negative 3, and x equals positive 3. Let's put a horizontal mark at each of these values to remind us to form a horizontal tangent line at these numbers when we sketch the graph of y. In the first interval, we need to draw y so that it is increasing and concave down and finishing out at a horizontal tangent line. So here we go. Increasing, concave down, and rounding out at a horizontal tangent line. In the next interval, we need y to be decreasing and concave down. No horizontal tangent line. Decreasing and concave down. In the next interval, y is decreasing but concave up and finishing at a horizontal tangent line. Decreasing, concave up, and rounding out at a horizontal tangent line. In the next interval, y is increasing and concave up. No horizontal tangent line. Increasing and concave up. In the next interval, y is increasing but concave down and finishing the interval at a horizontal tangent line. Increasing, concave down, and rounding out at a horizontal tangent line. In the last interval, y is decreasing and concave down. And that's it, decreasing and concave down. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.